So, an example for our thermal expansion, thermal stress problem. What we're going to do here is we have this post or bar or what have you. It is mounted to one rigid wall. It is 1 meter long, and at the start there is a 2 millimeter gap between the end of the bar and this wall. So we are starting at 25 degrees Celsius, and I'm asking at what temperature does the gap close, and at what temperature does the average stress in the post reach its yield stress. So we're going to be asking for two materials, looking at stainless steel 308, 304, and 6061 T6 aluminum. So we'll start off with the stainless steel. So here we've got our formula for the thermal strain. So we've got the coefficient of thermal expansion and just our delta T. And that gives us our delta L over L, which is our strain. For the particular alloy of stainless steel, the coefficient of thermal expansion is 17 microstrains per degree centigrade. I don't know why I almost said centimeter there. That's silly. Anyway, so we know that when we want to close this gap here, we know that the elongation is going to be 2 millimeters, and we know that the original length is 1 meter. So 1,000 millimeters. So that gives us our thermal strain at that point, which we can just use to solve relatively simply for our delta T. So that'll be 118 degrees Celsius. So that gives us our temperature at the point which it touches as the 118 plus the 25. So it's touching at 143 degrees Celsius. So for the next part, the assumption we're gonna make an assumption here. We're gonna assume that there's no change in yield strength due to the temperature change. Depending on how hot this thing gets, that may or may not be a reasonable assumption. But we weren't given. We're just given a number when we looked up. Well, haven't looked it up yet, but when we do look it up, we're just given a number. We're given like a function of temperature, so we've got to work with what we've got. So we know that the total strain is going to be equal to the enough to close the gap, and it's not going to move past that. So that'll be equal to the thermal strain plus the normal strain. So if we're working here at yield, the normal strain is just going to be equal to the yield stress divided by its Young's modulus. So for that particular alloy, we're looking at a yield stress of negative 207 megapascals divided by 193 gigapascals. So for a negative strain of 0.00107. Now again, we're going for negative because this is the stress state's going to be compressive. We're basically, once it hits the wall and tries to expand further, the wall is going to push back. The strain due to the normal stress is going to be negative. So just plugging that in. So we got that. Move this over to the other side. Adds together to get that, and then divide by our coefficient of thermal expansion, and we get a delta T of 181 degrees Celsius. So again, plus our initial starting temperature of 25 degrees gives us a temperature at yield of 206 degrees Celsius. So essentially, and if we push the temperature past that, then basically what we're saying is that we're going to be inducing permanent deformation in the bar once it cools back down. So when it shrinks back down, it's not going to shrink back down to 1 meter only. It's going to be shrinking down to a bit less than 1 meter because we'll have induced some sort of permanent residual compressive deformation. So moving on to our aluminium. So again, same idea. We're just punching in different values here. So we've got our thermal stress here, which is going to be, again, the same amount. Got just different value for our coefficient of thermal expansion. So that'll be at 108 degrees Celsius. It's going to be touching a bit sooner than the other one because it expands faster due to the higher coefficient of thermal expansion. So it does expand faster, but it doesn't necessarily yield faster. So if we get when we look at our total strain, that is limited to this amount, and again it's equal to our thermal strain plus our normal strain. Again, still punching in the values. The yield stress divided by the Young's modulus gives us negative 0.00421. So essentially what we're saying here is that despite the fact that the yield stress for the material is the yield stress for the material is kind of on par with the steel, but the Young's modulus is a lot lower than for the steel. So basically, it stretches a lot more before it starts to yield. It's more flex. It's a less stiff material, so it's able to deform a lot more before it starts to yield. So essentially, what that means is that it can the thermal stresses that would otherwise, the thermal strain that would otherwise be induced before it starts to yield is a lot higher. So it's able to, so essentially when we put, so despite the fact that it's expanding faster, it's expanding at 24 microstrains per centimeter, degree centigrade. I really hope I stop doing that. Despite the fact it's expanding faster, it has more room to expand before it starts to yield. Basically, it wouldn't, it doesn't need to be pushed as hard because it's less stiff. So it's not going to reach the level of stresses as fast. So its delta T there ends up being 259 degrees Celsius, and the temperature at yield therefore is 284 degrees Celsius. So it's heating up a bit more before it starts to yield than our stainless steel post would. And that's that for this example.